Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To give an introduction to this topic. And this is going to be a fairly basic introduction. We want to set the context, introduce some common terminology, introduce some of the key concepts, but I won't be going into depth into any of these things. And you will see an in-depth description of many of these topics in the later lectures to come. So again, so some of this material may be quite basic and redundant for some of you, and I apologize for that. So before jump into the actual lecture, I thought I'd start out with a kind of a puzzle. So let's say this is a fortified city, and you want to attack this city, and you have multiple armies at your disposal, and these armies have set up base camps all around the city at different locations, and what you want to do is attack this fort in a coordinated fashion. The idea is that if all these armies attack the fort at the same time in a coordinated fashion, then you are sure you'll win. But if even one of the armies does not participate in the attack, you're not going to be strong enough to overcome the enemy, and you are going to lose. So you want to make sure that all of you attack together, or you don't attack them at all. So as I said, you have these different camps, and each has each military army has a general, and let's say you want to decide whether to attack them tomorrow or not. The different armies may or may not be ready to attack the enemy. And but even if you are ready, the others may not be ready. So you need to find out if all the armies are ready and willing to attack. And so the goal is to make this decision whether to attack the enemy or not. And the only problem is this is back in the old days where you don't have the modern communication tools. So you can communicate with each other only by sending messengers. The problem is the messengers you send may not reach the other camp. They may be attacked by the enemies, captured, and so you have a problem. And you need to communicate with each camp and decide whether to attack the enemy or not. And remember, you have to make sure all the generals reach the same decision. They either all decide to attack, or they decide to hold off and not attack at all. You don't want some of them attacking and the others not attacking. So this is the puzzle. So with that puzzle, let me move on to our lecture. What is distributed computing, and why are we interested in this? So let me start with a very simple definition of distributed computing. Let's just say it's the use of multiple computers to solve a computational problem. This is a fairly broad and generic definition that covers several variations of distributed computing. So we'll see more specific formal models later on, but let's start with this basic idea. And distributed computing offers several advantages. So it gives us performance and reliability at a low cost. And so reliability is, well, basically if one or more of these computers go down, hopefully your system can still keep functioning because you are using multiple computers, and thus you gain reliability. You are able to overcome the failures of individual computers. And performance, again, the idea is here, commodity hardware is fairly cheap, and it's much easier and cheaper to buy, let's say, 100 commodity machines that give you performance P each, rather than try to get a single machine that gives you 100 P performance. You also have elasticity. That is, if you need more computational power, you can simply add more and more machines and hopefully get more computational power. And so these are the various advantages that distributed computing offers. So who wants all this computational power? Well, of course, there are many contexts where you want a lot of computational power. One context is, let's say, if you are running a website that's visited by, say, hundreds of thousands of users or millions of users, then you really want many of these features. You care about things like scalability, throughput, low latency, and so on. So specifically, there are, in fact, studies. I think I remember seeing some statistics which show how latency has an effect on users. So in particular, if you are an e-commerce website, there are some studies which show that if your latency starts exceeding something like half a second, it has a noticeable effect on users and on your revenues. So as latency increases from like half a second to 1 second or 2 seconds, there is actually a drop in the revenue you can make off from the users, because as a user, you are looking at the website, you want instantaneous answers, and if you don't find it, you get bored, you leave, and so you have all these users who want answers instantaneously when they use a website. And on top of that, I guess the other big buzzword these days is big data. Thanks to all of these users and to all these other phenomena, the volume of data that's being captured and is available for analysis is increasing dramatically. And again, people hope there's a lot of money to be made off by analyzing these data quickly and making decisions based on these data. So there's a lot of need for high performance of this nature. And there's another factor which makes distributed computing a very interesting and relevant topic today, which is that now you have access to virtual distributed computing infrastructure at fairly low cost at your fingertips, thanks to providers like Amazon, Microsoft, Google, and so on. So, I mean, previously, if you wanted to build some distributed system yourself, well, it was fairly complicated. You would probably have to buy all these machines, set them up, find a place for them, connect them, administrate them, and so on. But nowadays, you can do all of this just using a laptop or desktop from wherever you're sitting. It's all available at your fingertips. And so, in some sense, all of these factors come together and make distributed computing a very relevant topic these days. Now, even though these platform providers provide access to distributed computing infrastructure, building distributed systems is non-trivial. It's highly non-trivial. There are a number of challenges, and this is a discipline that has been around for 3 decades at least. People have been working on many of these problems, and you'll be hearing about a lot of this work over the next 2 weeks. So now the basic idea, I mean, the main challenges, I mean, your goals when you're trying to build a distributed system or any system for that matter is, first, you care about certain properties like correctness, consistency, and people also refer to them as safety properties. And what do I mean by this? Well, so if you have an e-commerce website, for example, a customer places an order, you don't want to end up charging the customer twice, the customer's credit card twice, for example. That would be a bad thing. Or let's say if it's a train reservation system, people are trying to book seats on a train, and you don't want to sell the same seat to two different customers. That would also be a problem. So these are all the kind of properties that people refer to as correctness or consistency and safety properties. But on the other hand, you also care about performance-related properties. You will also hear terms like progress and liveness guarantees. And so for example, again, if you are trying to make use of some service, what kind of guarantees do you get in terms of your ability to get the thing done? So I'm sure we have all at different points had frustrating experiences at websites where maybe you're trying to do something important, you're trying to log in into your bank account to get something important done, but you are unable to log in, something is going on, and all you see is a clock symbol or something like that. And roughly, basically, the correctness properties basically say nothing bad happens. And on the other hand, progress, liveness guarantees say something good is guaranteed to happen. Sometimes you may want stronger properties which say everything good that you want to happen will eventually happen. So your goal is to make sure both of these kind of properties are satisfied by the system. So what makes it hard? Well, one of the things that makes it harder in the distributed computing context is failures. Specifically, if you're going to build a system, you need to consider the computation model you're going to use. And as part of the computation model, you have to consider what the failure model is. What kind of failures do you assume can happen? And can you meet your goals, both in terms of correctness and progress, even in the presence of such failures? So in some sense, so the bottom vertex denotes the kind of assumptions you are going to make about the platform on top of which you are building. And the top 2 points indicate the guarantees you want to provide in terms of your system. And it turns out this can be quite challenging. And so in fact, for example, like around 10 years back, Brewer proposed something that's called a cap theorem or a cap conjecture, which says, in fact, in presence of failures, meeting both consistency and progress guarantees is hard. So the cap, the 3 initials actually stand for consistency, availability, and partition fault tolerance. So in fact, there's a older result in the distributed computing literature which says a specific primitive that's very important in distributed computing called consensus, in fact, is impossible to achieve in the presence of failures. So we'll get to this in more detail later on in this lecture and in several other lectures in the next 2 weeks. But the starting point for all these problems is concurrency and parallelism. So let me start with a quick introduction to this topic of parallelism, especially in the context of a shared memory parallelism. This is probably one of the simpler models of distributed computing. And this is something you have in your, this is the kind of program you can write and run in your own desktops and laptops because thanks to multi-core architecture, you already have some sort of parallelism in your machines these days. So what you see in the slide here is a toy parallel program. So the semicolons denote sequential composition. They indicate that the statements are executed one after another in sequence. The parallel line symbol indicates parallel composition. It basically indicates these 2 statements are to be executed in parallel. And so if you take this program, if you run it, what will the final value of result be? Well, you can stare at the program. It's fairly trivial. It's a toy example. It's clear if you execute this program, x is going to get the value 2, y is going to get the value 2, and when you execute the final statement, result is going to be 4. So just as a digression, just in terms of the notation, in case it's a little bit confusing, if you've written parallel programs using, say, Java, C#, you've probably written more complex code, and I'm just using shorthand notation to indicate parallel composition. So the code fragment written in this fashion, in fact, can be thought of as shorthand for this kind of code, which is what you might write in Java, where you create threads to execute some computation, you start the threads, and then you wait for the threads to complete execution. So there's all this mechanism to run parallel code, but in the end, your goal is to run these two statements in parallel. And so now we get to a slightly more interesting example, which is very similar to the previous one, but here, let's say the program is, you have a variable that is initialized to 0, then you run these two computations in parallel, each of this which increment x by 1, and finally you look at the final value of x. So what's the final value of result going to be? So, well, just to make things interesting, let me stop at this point and ask if people have any answers to this question. One or two is one of the answers. So what do others think? Let's say you use a compiler to compile this program. The single statement to increment x can actually be broken up into multiple, let's say, machine instructions. So for example, the code generator might look like this, where you load the value of x into a register, you increment the value of the register, and store the register's value back into the variable. And the problem is, in general, these two code sequences can be executed in an interleaved fashion in many different ways. So how the instructions of the left-hand computation and the right-hand side computation are interleaved can actually determine the final result. So let me not go into the details here. So the final result really depends on what sort of code the compiler generates and what kind of interleavings are possible. For example, in terms of terminology, we often say there's a data race in this parallel computation, where one of the threads is reading the value of x while the other thread is updating the value of x. And now there is these two computations can happen in either order. And so now if you look at this computation, and in principle, it is in fact possible for them to execute and produce a final value of 1, as somebody said earlier. Now that is clearly undesirable. Something seems wrong here, right? So because the way we think of this program, you increment the variable and you did it twice in parallel, but you expect the final value to be 2, not 1. And so one of the problems or challenges we run into this context is that we need to avoid undesirable interleaving of code by, in some way, we need to ensure that critical piece of code are executed in a mutually exclusive fashion to avoid undesirable outcome. So basically, concurrency or parallelism introduces this challenge, that you have non-determinism in the order in which code fragments can execute, and this non-determinism can introduce potentially undesirable effects. And so one of the challenges, if you're writing parallel programs, is concurrency control. You somehow need to ensure that code fragments that can potentially affect each other execute in a desired order, and you also need to ensure isolation. That is, make sure they somehow don't interfere with each other. And you have to do this while ensuring that individual threads can make progress in their computation. So one solution, again, if you're writing programs using Java or C# on your machines today, you might often have used as lock-based synchronization. Right. So let me just go through this notion of locks in case some of you are unfamiliar. So a lock basically offers two primitives. One is to acquire a lock, and the other is to release a lock. And what does it guarantee? Well, it makes sure two threads cannot acquire a lock at the same time. So initially the lock is not acquired by any thread, and if a thread executes a acquire instruction, it will successfully acquire the lock and it can proceed. But meanwhile, if some other thread tries to acquire the same lock, it will be blocked from executing. It will have to wait until the lock is released before its attempt to acquire the lock succeeds. And so for example, if you add concurrency control using logs to this code fragment in this fashion, this guarantees that the two increments cannot interfere with each other, and it guarantees that the final result value will be 2. Okay, so now there are, however, some drawbacks with locks. First, programming with locks in general is hard, and if you and in fact it kind of, there are challenges with respect to both safety as well as progress that locks pose. If you use too little locking, you can introduce correctness bugs. So if you go back to the previous example, instead of increment, right, in general in a realistic system, other things could be happening. So for example, two different customers might be trying to buy a ticket on a train, and if you don't use appropriate mechanisms to ensure isolation, you can end up selling the same seat to both customers. Right? So too little locking and you end up with correctness bugs. If you use too much locking or don't use it appropriately, you run into other problems like deadlocks. Deadlock is a situation where threads cannot make progress because all of them are waiting to acquire a lock that is being held by some other thread. So for in the simplest scenario, you have two threads. Let's say thread 1 acquires lock 1, thread 2 acquires lock 2, and then thread 1 tries to acquire lock 2, and thread 2 tries to acquire lock 1. Well, now both are stuck, both are going to wait forever and not make any progress. Even if you don't have deadlocks, you have other concerns like starvation and fairness. So for example, even though system does not actually deadlock, it's possible some thread does not make progress because it's continuously waiting for some resource. And finally, even if you don't have specific theoretical concerns like deadlocks or starvation, you could have performance concerns. Blocking could slow down your system. And finally, locks are actually uncommon in true distributed systems. We have been looking at simpler shared memory parallelism, and so when you move into true distributed systems, you'll have to use, you'll often try to use solutions that don't rely on locks. So now the problems we have encountered with parallelism and concurrency is of course not a new problem. This problem has existed for several decades, and in fact back in the 70s the database people came up with solutions to this problem based on the notion of transactions. So let's say you want to build a system, and that's going to be used by a large number of concurrent users that are going to interact with the system. So for example, this could be a reservation system, and all the users are trying to use the reservation system to make reservations, cancel reservations, whatever. Right? So now when a user interacts with the system executes some code on behalf of the user. Let's call this a transaction. And when you have concurrent users, the transactions being executed on behalf of different users can execute in an interleaved fashion. So in this figure here, what you see is, let's say the numbers refer to, say, individual instructions executed by transactions. And the blue instructions are executed by a transaction corresponding to one user. The yellow instructions are instructions executed by a transaction corresponding to a different user. And just as we saw earlier, now this interleaved execution could produce undesirable behavior. So the database people came up with a notion of correctness that you want in this kind of setting. So, and this notion is based on something called serializability. The idea is, if no matter how these transactions actually execute, if their execution is actually equivalent to a non-interleaved execution, let's say, by non-interleaved execution, I mean these two other executions down below. In one case, the blue transaction executes completely before the yellow transaction executes. And in the other case, the yellow transaction executes completely before the blue transaction executes. Now, if the effect of the interleaved execution are exactly identical to one of those other two executions, then we say that the first execution is serializable. And what databases try to guarantee is serializability for transactions. So, so you might have heard of this acronym called the ACID properties of a transaction. So the database people actually enumerate several desirable characteristics for transactions. The acronym ACID stands for atomicity, consistency, isolation, and durability. So atomicity basically means that either all or none of a transaction's effects must take place in the database. So for example, if you have to abort the transaction for whatsoever reason, then there should be no effect. So you can't do half of a transaction. So for example, if you're doing a commercial transaction, charging a credit card, placing an order, and so on, you can't charge the credit card and then not execute the other part involving where you actually place the order. And atomicity and isolation are the most interesting parts here. And isolation basically says it must be as isolation corresponds to the notion of serializability we saw in the last file. It basically says it should be as though transactions executed in isolation without anything else happening at the same time. And the other properties are perhaps less interesting in our context right now. So durability just says the effect of a transaction must persist forever. If you execute a transaction, it is successful, its effects must not suddenly disappear at a later time due to some failure. Yeah. Yeah. Same.
Like here, the blue and yellow instructions, they are pretty isolated. Like it's like the blue. There's no overlap between the instructions that different users are.
Okay, so your question is what happens if two instructions execute at the same time?
Two different people try to execute the same instruction.
Okay, right. So I'll phrase that question as saying, let's say the instruction 3 being executed by one transaction and instruction 4 being executed by another transaction. What happens if they execute at the same time?
No. The question is, if instruction 3 is being executed by person A and by person B.
I think he's saying the instruction 3 and 4 in this particular case are the same instruction. What will happen?
So,
My question is, there are two users, A and B. What happens if both of them want to execute the same instruction?
Right. So the yellow guys are executing instructions labeled 2, 3, 6, 7, and 9, right?
Yeah.
The blue guy is executing instructions labeled 1, 4, and 8.
Yeah.
Are you saying that some of the blue labels have the same value as some of the?
Yeah.
That's what I said.
Right.
Assume, for example, that 3 and 4 are the same.
Right.
3 and 4 are the same instructions.
right. So they can be the actual same instructions, but still they are going to execute twice. Once on behalf of transaction 1 and once on behalf of transaction 2. So when I say instruction, I mean the actual occurrence or execution of an instruction. So these numbers are giving identifiers to the specific execution of instructions by transactions. So in fact, these two transactions could be the same transaction in the sense of code being executed in parallel, but then it is executing twice. So the same instruction will execute twice, and we give them different names in this context just to. Right. So, so the notion of serializability, ACID properties, formalize the kind of guarantees or the correctness properties you want for these transactions. But the database people also came up with implementation techniques to guarantee these kind of correctness properties. And there were actually, broadly speaking, two families of approaches. One based on locking and is referred to often as pessimistic concurrency control. And this tries to prevent undesirable interference from happening in the first place. So, for example, what you want to ensure is isolation, and locking the database transaction implementation make sure there is no semantic violation of isolation. And there are specific locking protocols you can use to make sure you avoid deadlocks and make sure the system makes progress as a whole. And so that's one family of approaches for implementing transactions. But there's also another approach based on another category, which is often referred to as optimistic concurrency control, where you don't actually use locks. Instead, intuitively you let the transactions execute in parallel. But what you will do is you will detect whenever two transactions execute in such a fashion that you don't have serializability. There is a violation of isolation. And when you detect that, you will take steps, corrective steps, use rollback mechanisms to undo a transaction's effect and re-execute it. So these two have slightly different characteristics. So optimistic concurrency control is doesn't use locking and is often referred to as non-blocking. So what this database work gives us is, first, it gives us a generic correctness criterion in terms of serializability and the ACID properties. What do I mean by generic? In that it's not a correctness property for a specific application, but it's a correctness application that can be applied for any application. And so let me expand on that in the next file. But the database implementation techniques also give us generic automated implementations that can achieve these properties without the programmer actually having to worry about all of this. And as I said, guarantees safety and some sort of progress guarantees, actually depending on the kind of implementations used. So it looks like the problem has been solved, and that is true, but in a certain setting. So for example, in the context of centralized databases, the database implementations take care of all of these problems for you, so the database programmer doesn't actually have to worry about all of these things. So at this point, let me say, so this notion of serializability was refined in some ways in the 1980s. In particularly, Herlihy and Wing came up with the notion of linearizability, and Maurice Herlihy is one of our speakers next week. So, now, if you go back to the definition of serializability we looked at just now, it's stated in terms of the execution of the transactions which is inside the system. So, one of the key ideas, critical points in this notion of linearizability is, first, to forget what happens inside the system, which is an implementation detail, but let's just look at how the rest of the world interacts with the system. Right? So in this case, I have dropped the execution of the transactions, and what you see here are just these blue and yellow arrows going inside and out of this box. So you can think of this as this captures how the rest of the world interacts with this box. right? And this is often referred to as a history. And a history consists of multiple events. The arrow going inside the box is a call event. You are initiating some transaction or an operation, and the arrow coming back out of the box is a response event. And in general, a history consists of interleaved call events and response events. So, one of the critical ideas in this definition of linearizability is to now state correctness in terms of saying that this observed behavior, if this is the observed behavior, then either ACBD or BDAC should be a correct sequential history. In this case, we say this execution history is linearizable. Here, the notion of a correct sequential history is determined by a sequential specification. So what do I mean by that? So the idea is, we assume you can define what the desired correctness property is for sequential executions when there is no interleaving or overlapping of operations. So in this, what you have is a sequential history where any call event is immediately followed by the response event for that call event. There is no interleaving, and it's fairly easy and straightforward for people to define what the expected behavior is when you have only sequential execution, no concurrency, no overlapping. Given such a sequential specification, then we can define what it means for an interleaved history to be correct. And so linearizability is basically a formalism for defining correctness of concurrent objects. By concurrent object, I mean you can use this idea whether you are trying to build a system like a train-reservation service which is interacting with the external world consisting of users, or whether you are building some component like a set or a map or a data structure that's going to be used by other code. The setting doesn't matter, but in either case, what you have is a component that interacts with the rest of the world, and the notion of linearizability gives us a way to define correctness for such objects. And so there is one other distinction between the notion of linearizability and the notion of serializability we saw earlier, which is that linearizability is a strict serializability. That is, it requires the order of non-overlapping operations to be preserved. In other words, serializability as defined earlier, actually, if you consider an interleaved execution, you could have multiple overlapping transactions. So you could have a transaction 1 which overlaps with transaction 2, transaction 2 overlaps with transaction 3, but transaction 1 and 3 may not overlap. All right. But the notion of serializability allows the end result to be as though transaction 3 executed before transaction 1 executed. And this can lead to unintuitive behavior in some contexts. So the notion of linearizability says, well, the system should ensure that the order of non-overlapping operations is preserved. So in summary, if let's say theta is a sequential specification, linearizable theta can be thought of as a concurrent specification. It's a specification for what is correct in the presence of interleaved executions. And in the same way, serializable theta is also a concurrent specification. I mean, you could phrase it in this way, though it was not done so originally. And again, you will hear more about all of this in Maurice Herlihy's lectures next week, so I won't go into more detail at this point in time into all of these notions. So the notion we saw now just talks about correctness, but as I said earlier, you also worry about progress and liveness guarantees. And so in this abstracted notion of linearizability also led to a couple of notions like lock free and wait free. So I'll again just give the intuitive notions of what these terms mean. You will see a more formal definition next week. So the notion of lock-free just means at least someone should make progress. It's similar to the notion of deadlock freedom in the blocking world where you use locks. The notion of wait-free says that everyone should make progress, and it's similar to the notion of starvation freedom in the context of locks. Subsequent to these notions, in the 90s and even in the last decade, there was a lot of work in designing non-blocking algorithms and data structures that for linearizable concurrent data structures. Again, you'll see examples of this in Morris's lecture next week. So I won't go into that. So now the notion of transactions was also refined in some ways in a programming language context in the last 2 decades. We have a notion called software transactions. So software transactions, actually, the idea is to make the transactions as a first-class programming language construct in a programming language. The notion of transactions as it existed in the database world, you have, let's say, 2 different systems. One is the database, which can execute transaction. The other system executes interacts with the database by executing transactions. But in the programming language context, you embed the transaction as a language construct. Maybe an example will make it easier. So if we go back to the earlier example we had, it would be nice if instead of having to talk about locks and implementation mechanisms, you simply enclosed this code fragment and say this code fragment should execute atomically. Here the keyword atomic is used in a programming language context often to denote what is called isolation in databases. So in a programming language, this simply says these 2 code fragments labeled atomic should, no matter how the system actually execute, it should be as though they executed without any overlapping. And in this case, you will get the correct desired behavior. So again, you'll hear more about software transactions and their implementations in Tim Harris's lectures later in this week and next week. So now just to go back to the picture we had earlier. As I said, normally when we build the systems, we care about safety properties, we care about liveness properties, and you want to guarantee these in some computation model. And what we have seen so far is, you've seen how you can specify desired correctness properties using notions like linearizability and serializability. There are notions like lock freedom and wait freedom relating to liveness and progress kind of guarantees. And so in this context, as I mentioned earlier, theta is a sequential specification. So when I say sequential specification, you can think of that as a specification for a sequential data structure, let's say, like a set or a map or a stack, queue, whatever. All right. So as I said, it's possible to design data structures that are specific, data structures and algorithms that are specific for a theta, like a set or a map, that achieve the desired properties. These are the, as I said, you'll see examples of non-blocking data structures and algorithms that achieve some of these guarantees for specific data structures like lists and sets. But it's also possible to use generic algorithms like transactions. What do I mean by generic here is that the notion of a transaction is actually quite powerful. It's not for a specific data structure like a set or a map. It lets, if you have transactional capabilities, you can write almost any code and have it execute atomically in isolation without interference. But as I said earlier, much of the things I've been talking about so far has been in the context of a specific computation model, namely shared memory. But there are several different computation models in the distributed computing world. So let's go through these different computation models at this point in time. Let me start out by fleshing out the notion of shared memory a little bit at this point. So specifically what we've been using is something that's referred to as an asynchronous shared memory system. In an asynchronous shared memory system, you can assume you have a set of computers. You'll see terms like process or processor or a node being used to refer to these things. I'll often use the term process. Now each process can have its own local state or memory, basically, which is private to the process. But in the shared memory model, you assume there is a shared memory that all of these processes can access, and they can do so using various kinds of instructions. So in fact, there are very specific models you can obtain by restricting what kind of operations are permitted in shared memory. Typically, the kind of operations you see are things like, of course, the most obvious things you do is to read and write the values of locations or variables in the shared memory. But you gain more power when you move on and have instructions that in a single instruction let you basically read, modify, and write. So examples of this are things like compare and swap, which is often referred to as a CAS operation, which this operation actually specifies a new value for a variable, but it also specifies an old value for the variable. And this instruction will check the value of the variable, and only if it has the specified old value will it be overwritten by the new value, and the instruction returns a status indicating what happened. But if the current value of the variable is different from the old value specified in the CAS instruction, then the instruction does nothing. And there are other other read, modify, write kind of instructions. The simplest is test and set, which applies to Boolean variables, which sets the value of the variable to a particular value, but it also returns its old value. And swap is similar to test and set, but applies to arbitrary non-Boolean variables. And in fact, it turns out there are interesting differences between the computation models you get depending on what kind of instructions you allow. And you'll hear more about this in the lectures in the next 2 weeks. And so I guess maybe the final thing to talk about is this word asynchronous. What this really indicates is that here we don't make any assumptions about the speed at which the different processes execute. So one process may take 1 day to execute an instruction, the other process might be executing instructions very fast. And so in this model does not allow the programmer to make any assumptions about the speed at which these processes will execute instructions. So now, so that's the model, and as I said, one of the complicating aspects of distributed computing is the notion of failures. The kind of failures you see in asynchronous shared memory model are basically what are referred to as process failure. And there are 2 kinds of process failures. One is a stopping failure. So in a stopping failure, you assume a process simply stops executing, and it's as if the machine has crashed, and that's it. It won't participate anymore in the ongoing computation. And you'll hear terms like a faulty or failing process for this kind of process, and we'll use the term correct or non-failing, non-faulty for a process that does not fail throughout the execution under consideration. So remember that the notion of correct process is relative to a given execution, and in that execution it never crashed. However, there's a more complex sort of failure that could happen that's referred to as a Byzantine failure. In a Byzantine failure, you assume the process can actually start executing arbitrary code. Remember, you design the algorithm and expect the process to implement the algorithm you have designed. When a Byzantine failure happens, we assume. So Byzantine failure, for example, is intended to capture malicious behavior. So for example, if a virus or some malicious software takes control of your computer, some attacker has taken control of this and they can make it execute their own code. If that happens, it's much harder to deal with. So the word Byzantine failure refers to this kind of failure. Once failures come in, when you formalize the desired progress conditions, you have to refine it in some fashions. So for example, examples of the way you would refine it is to say, as I said, you might have a progress you might want a progress guarantee that every process makes progress, but obviously if a process has failed and stopped executing, it can't make progress. So you would settle for a qualified progress guarantee which says every non-faulty process must make progress. And there is also a notion of fairness you use in these executions. So for example, when you formalize an execution, you can think of an execution like we saw in the earlier examples as a sequence of individual steps, where each individual step is an individual step or action taken by a single process. Now in this context, if we don't allow a process to execute at all, again, then you can't expect progress. So you use a notion of fairness to qualify the kind of progress guarantees. That is, assuming that processes get enough opportunities to execute whatever steps they want to execute, then you would like to ensure progress. So just to kind of relate this to some of the earlier discussion about locking, as an example, let's see what happens if you're using locks in your algorithm and a process that's holding a lock fails. Well, then any other process that wants to acquire that lock will be stuck because it will wait forever to acquire that lock, but the other process has failed, so it's never going to release the lock. So this is why locking is referred to as a blocking operation. And so this, for example, will make it hard for you to achieve progress guarantees. And this is one of the reasons when you have failures, you want to design algorithms and data structures that don't rely on locks. Okay, so much for the computation model called asynchronous shared memory. Let me talk about a second model, which is referred to as an asynchronous network now. So in an asynchronous network, just as in the previous case, you have a set of computers or processes. But while in the shared memory, you had a shared memory for process to communicate with each other. In this setting, there is no shared memory. Communication instead happens via messaging. And messages, again, there are different assumptions you can make about the messaging, kind of messaging facilities you have. One common model is to have point-to-point messages. So one process sends a message to another specific process, but you can also have broadcasts where a process sends a message to all other processes, or you could have something in the middle called a multicast where a process sends a message to a subset of processes. And the model often can also be, you could make assumptions about the network topology. So you could try to build algorithms that work for specific restricted topology, or one common situation you see in many algorithms is you just assume it's a completely connected graph. So any process can send a message to any other process. So, and we use the word link or channel to refer to a communication channel between two processes. And in this model, you have process failures just as before in the shared memory setting. It's more or less the same. But here you have also the possibility of channel failures or link failures. Specifically, the assumptions you can make, there are a number of different assumptions you could make about the messaging system, ranging from strong assumptions to very weak assumptions. At the strong end, for example, the notion of reliable FIFO says that you assume messaging is reliable. Every message that is sent by a process will be received by the receiver, and messages will be delivered in the same order in which they are sent across a channel. Starting with this strong model, you can weaken this model in various ways. So you could have a reliable channel with reordering, where you assume any message that is sent will be reliably delivered to the recipient, but you assume that messages may not be delivered in the same order in which they are sent. Then you can introduce more and more kinds of failures. So you could, one of the other kinds of failures is message failure, message loss, where a message is sent but never received by the receiver. You could have message duplication, where the same message is sent, received more than once. And you could also, there are models where you try to do something in the middle, where you limit the messaging loss in various fashions, where you assume messages may be lost but not forever, and so on. Okay, so the third model I'll briefly mention is the notion of a synchronous network. A synchronous network looks very much like the asynchronous network. Again, you have a set of processes. They form a directed graph. The edges of this graph denote communication channels or links. And every process has its own state, which is the local state. But the difference here is we assume the system executes in lockstep. So every process simultaneously executes one step. And in this one step, they look at the incoming messages on all incoming channels. They look at all the incoming messages and their local state to determine what kind of transition they are going to make. So they'll transition to a new state, and they'll place an outgoing message on each outgoing channel. So this is a sort of an automaton. And what I just described is what is referred to as one round. So the whole system executes in rounds, one after another. And you can introduce, just like in automaton formalisms, notions of initial states and halting states to formalize computations in this model. So now, if you look at this, yeah.
This you're assuming that each node will do the round simultaneously,
Right. Each round consists of all processes taking one step, and in that one step, all of them look at all incoming messages and their current state, determine what kind of transition they want to make. They move to a new state, and they place an outgoing message on every outgoing edge. It's so now actually an asynchronous network captures, in some sense, the broadest class of distributed systems. When I say broadest, I mean an algorithm designed for asynchronous network can be used in almost any context because it makes the least assumptions. It doesn't assume there's a shared memory or so in a sense that's a most realistic model. Now both the asynchronous shared memory and the synchronous network make one simplification in a different direction each. So asynchronous shared memory adds a shared memory for communication purposes. On the other hand, synchronous network instead assumes all processes execute in lockstep. So I place them slightly differently to indicate that synchronous network is perhaps a less realistic model. right? It's a useful model when you are designing algorithms because it helps simplify development of algorithms and so on. But on the other hand, both asynchronous networks and asynchronous shared memory are somewhat realistic. I mean, are both realistic in the sense you can really find instances of this. Of course, asynchronous shared memory, as I said, you can find even in a multi-core machine is sort of like asynchronous shared memory, but that's in the context of a single laptop or a desktop. And if you really want to put together large number of computers together into a distributed system, then you end up with the asynchronous network, which so now going back to the summary we had earlier, what we saw was so earlier we discussed the notion of transactions and said, well, database transactions sort of solve this problem, but in a particular setting, namely in a centralized database setting, in a shared memory setting, and so on. So again, so maybe at this point, it's one point worth stating is that when you design algorithms and want to make formal claims, one desirable property often is that you want to ensure safety in all cases. That is, but then you would like to make liveness guarantees subject to some assumptions. So, for example, if you consider messaging and I guess one thing I didn't say is often you do not assume anything about how much time it takes for a message to be delivered in the asynchronous network setting. In contrast, the synchronous network setting, in fact, makes this simplifying assumption really about message delivery, that in one step the message is also delivered. Right. So if you are designing an asynchronous network algorithm, you typically don't make assumptions about how much time it will take for messages to be delivered, and regardless of how much time messages take to be delivered, you would like to guarantee safety. But your progress and liveness guarantees may depend on message delivery times and so on. So anyway, so as I said earlier, transactions sort of solve the problem in a simplified setting, in like a shared memory setting where we ignore failures and so on. The problem is once we move into settings like asynchronous network with failures and so on, that complicates things. And so in particular, you can show certain kinds of things cannot actually be achieved in the presence of failures. So when you are trying to establish a lower bound of this form, it's useful to take simple problems and show they cannot be achieved. So the consensus problem is an example of a simple primitive that's very useful and often seen in the distributed computing context, but it turns out to be actually a hard problem. It's also referred to as an agreement problem. And so the problem statement is this. You have a set of processes, each starts with a value, let's call it its input value, V. Now every process wants to finally settle on an output value. It's trying to decide on an output value, subject to these conditions. The word agreement is used to denote that no two processes should decide on different values. In other words, loosely speaking, you want all processes to agree on the to decide on the same value. Except when I say all, we'll get to that in the termination context. But there's also a condition called validity, which says that the value decided by any process must be the initial value of some process. So actually, there are many variations of the consensus problem where, for example, you can vary the validity conditions in various ways. But for us, we can simply take this to be the notion of validity. And finally, you want a termination guarantee. That is, you want to say all non-faulty or non-filing processes eventually decide on a value. So if you think about it, this is a fairly simple primitive. What you want to do is take a set of values. Each process comes up with a value. and choose one value out of all of these sets. You want to make some non-deterministic choice out of this set of values, but you just want to make sure all the processes make the same choice. And so, in fact, so now the puzzle I presented right at the beginning of the talk, in fact, is an variation on this kind of consensus problem. However, it turns out that consensus is impossible to achieve in general. And by that, when I say impossible, what I mean is we cannot achieve the desired safety as well as progress conditions in the presence of failures. And you'll hear more about this in the later lectures in the next 2 weeks, where both about the impossibility result as well as, though it's impossible as sketched, obviously, as we'll see, this turns out to be a common primitive you need in many contexts. So you do need to implement something. And in practice, researchers have come up with various kinds of trade-offs you can make. You can, for example, try to make sure safety is satisfied and give up on liveness. And that is, theoretically, you may not have a liveness guarantee, but in practice, hopefully things work, and so on and so forth. Again, you'll hear about this in later lectures. So, so at this point, so we saw earlier, shared memory somehow simplifies things. So one natural question to ask is, well, if you have an asynchronous network, can't we simulate shared memory? So, for example, can't we simply let a process play the role of a shared memory? So, for example, you could imagine all other processes sending messages to this single process to read the value of a shared variable and getting a response back as a message. And basically, you replace the shared memory by a single process which acts as a shared memory. This can, of course, be done. Of course, this gives us the programming convenience of shared memory, but this is not going to magically solve the difficulties we have with the network in the presence of failures. So you will still inherit various failure characteristics of networks. So, for example, in this model, the process in the shared memory model, we assume that the shared memory never failed, in fact, right? So, but if you are using a process to serve as a shared memory, it can fail in the if you assume processes can fail. And furthermore, in a shared memory settings, read and write operations on the shared memory were like primitives. We didn't allow them to take forever. Whereas if you're doing it via messages, again, then you are constrained by whatever assumptions you make about the messaging system, whether how long they take. And yes. Sorry? The consensus. Deadlock. Yeah, deadlock is possible in shared memory if you use locks. Yes. But a deadlock is what happens when you use, what can happen if you use locks. So it's a characteristic of an algorithm, not a characteristic of the system, of the model. But you are right. If you are designing a system for shared memory, you have to make sure you don't run into deadlock. So, I didn't mean to suggest that designing things for a shared memory is trivial or simple. You have challenges even in the designing algorithms with good progress guarantees in a shared memory setting also. Difference? Well, that's a good question. As I said, in practice, you often you try to avoid locks in a asynchronous network system. You could use logs, but they pose so many challenges, and especially when you are going to make these failure assumptions. So yeah, in many of the algorithms you'll see you the next 2 weeks, in fact, you're not going to encounter locking or lock-based solutions. Now, there are, of course, distributed deadlock detection is a well-defined problem with well-defined algorithms. I'm not sure about their exact complexity of distributed deadlock detection. So, right. Okay, so now if you're going to simulate shared memory using a process, of course, you could do it with not single process. You could use multiple processes to simulate shared memory. So, in fact, this is also done in practice. And I mean, what you get here is basically distributed storage, which is actually a fairly fundamental requirement, or which, if it's available in your platform, it can greatly simplify writing your applications. Okay, so now let's briefly go back to this original kind of setting we had. Let's say you are trying to design an interactive system which will interact with a large number of concurrent users. One of the common ways in which you build such systems is using 3-tier architectures. And one way in which this could be realized is the following. So what you have on the top are these application servers, basically, that the users interact with. The application servers execute basically operations on behalf of the users. And you could have data stored in a shared database or some storage layer. And so, for example, the use of these application servers at the top level gives you scalability and fault tolerance at that level. Even if some of those processes fail, the system can keep going, and you can scale the system by adding more processes there, and so on and so forth. But of course, in a design like this, this centralized database could end up becoming a bottleneck. For example, well, if it can fail, then it will bring down the whole system, which would be terrible. Even if it doesn't fail, from a performance perspective, it could become a bottleneck. So in practice, there are multiple techniques people use to achieve scalability and reliability in this kind of setting. One is to use a notion of partitioning, also referred to as horizontal partitioning or sharding. And what you're doing here is actually kind of breaking up the database into multiple disjoint databases. Specifically, the data stored in each of those databases is different. They are disjoint. And so, for example, if you have a banking system, let's say you might decide to store all information about bank accounts numbered 0 to 10,000 in one server, and all information about bank accounts numbered 10,000 to 20,000 in another server, and so on and so forth. This is one way of kind of partitioning the space of data into multiple databases, and this also kind of partitions the users. And now, of course, this kind of partitioning, there is an interaction between partitioning and consistency. This kind of thing is conceptually simple if each transaction that a user wants to perform accesses only information in one partition. But however, let's say, for example, you want to do a money transfer operation where you want to transfer money from one account to another account, and let's say the information about the source account is in one partition, the information about the target account is stored in a different database partition, then you need to perform an operation that accesses multiple of these databases. And this ends up being challenging. So in this context, you run into, if from a transaction perspective, you end up having to do something like, say, a distributed transaction. If you want to perform this operation. And it turns out this sort of requires a consensus-like primitive, which we just saw was impossible. One of the other, so the horizontal partitioning, of course, is not going to immediately give you reliability, because the data for any specific atom is only in one database, and if that goes down, you are stuck for that piece of information. So the other key ingredient often used is replication. So in a replication, you replicate a database or a storage system multiple times. I've just shown 2 replicas, but in general you could have multiple replicas, and each one stores the same data. So different servers processes can access different replicas for their data needs. So this also poses a challenge. There's an interaction between replication and consistency as well. So just as an example, let's go back to our earlier example. Let's say you have a reservation system. 2 different users are trying to buy a ticket. There's only one ticket left, but suppose they access different replicas. In the end, you need to ensure only one of the users will successfully be able to make the reservation. Again, this is sort of like a consensus-like situation. You have to make sure in some sense, the system has to decide and agree on which one person will get the last remaining ticket, which is whose transaction executes first, basically. Again, so the replication also needs things like consensus. So in general, so the kind of thing we have been talking about, you think of them as distributed storage, right? It's and you can distinguish between different kinds of distributed storage. At one extreme, you could have something like a distributed database, which gives you full transactional capabilities, which actually simplifies the job of users of the distributed database. That is, if you have other processes executing using a distributed database, the database takes care of consistency requirements in some sense. But you can also build other distributed data structures that don't give you full transactional capabilities. So for example, you could have data structures such as maps or sets. So again, in a distributed setting, the notion of a key value store is a fairly popular and common one. So in the last decade, in fact, there's been a lot of work on designing various kinds of distributed key value stores or maps, basically. A distributed data structure basically gives you a limited predefined set of operations. So more efficient implementations are possible that exploit the semantics of the particular data structure and the operations. In this context, it also turns out people have also, as I said, the impossibility of consensus basically forces us to make a choice. And some people have actually made a choice where they give up a little bit on the consistency side. So they design data structures that give us weaker consistency. Again, you'll hear a lot more about this in several lectures later this week and next week. So specifically, if you look at replication specifically, which is one of, as I said, replication and partitioning are both 2 key ingredients of distributed data. If you look at replication specifically, you will hear the term replicated state machine, which is essentially a replicated data structure like a set or a map. That is, conceptually, you have a data structure, let's say a map. You want to maintain multiple replicas of this data structure, and it offers specific operations, like a map will give you operations to look up the value of a key and update the value of a key. And these requests can be sent to any replica, and you'll get a response from that replica. And the replicas have to talk to themselves and somehow ensure you have a correct behavior. So So as I said, replication is also a key ingredient, and you'll hear more about replication in later lectures. So actually, so that brings me to the end of my lecture. So let me stop at this point and answer any questions people might have. Hi.
So I have a minor doubt on the difference between serializability and linearizability. So is it that linearizability is a specification that allows that defines correctness with respect to a transaction given by a single user, irrespective or independent of the transactions that are being issued by other users?
No. So neither of these actually care about these users or make distinctions like that. In a sense, well, conceptually there are two key differences. Well, serializability as originally defined in the database setting in the 70s involved executions of transactions. They looked inside and talked about the individual operations performed by the transactions, and they required that if transactions interleave, then the interleaved steps should not somehow interfere with each other, right? But when you move to linearizability, you forget the internal details of how the operations execute. Instead, you take as the starting point a sequential specification. So if you take a set or a map, you can give a sequential specification that says what it means for sequential executions to be correct. So let's say if you take a stack, for example, let's take a stack. If I push the value 5 and then push the value 7 and do a pop, and if the pop returns 7, this is a correct execution sequence. But if I push 5, push 7, and then do a pop and I get back 5, then this is an incorrect execution according to the stack semantics. So a stack's sequential specification can be just thought of as a set of all legal sequential histories. So the two examples we saw, one is a legal sequence and the other is a legal sequence. So the notion of a sequential specification says what it means, which sequential execution or a history is legal. Now linearizability says if you have an interleaved sequence of operations, let's say I initiate push of value 5, I initiate push of value 7, I initiate pop, let's say, and then the first push completes, the second push completes, and the pop completes, and so this is an interleaved history, right? So we say this interleaved history is linearizable if I can rearrange the same invocation and return events into a sequential thing that happens to be legal according to the sequential specification. So specifically in this case, the one way I can reorder this is to say the push of 7 happened and it returned, the push of 5 happened and it returned, and then the pop happened and it returned 5. So so now so this is the basic intuition, but there is the actual distinction between serializability and linearizability comes down to one critical point, which is relates to the order of non-overlapping operations. So serializability, conceptually you could also formulate it in a similar fashion, though it was not done so in the 70s for databases, but you could adapt notion of serializability with a sequential specification. But serializability says if I have two overlapping operations, when constructing this legal witness, I am allowed to reorder them. But linearizability does not allow you to reorder these two non-overlapping operations. So is that? Hi.
Overlapping operations have to be defined in some way, right? So let's say we define in terms of the professor or
it might not make sense for the operations. So it might not make actually some sense for the operations to be related to the real time, but it might make sense to, let's say, order it according to some let's say happens before ordering, something like that. So it's not always like necessary to relate the ordering to the real time, right?
Yeah, so yes and no. I mean, so abstractly, all of this is with respect to a notion of a history. And a history itself, we simply define as a sequence of events. The event can be either an invocation event or a response event. And so mathematically, that's it. That is, we don't have to worry about time at all. But of course, implicit in this ordering is the idea that the events happen in that time order. That's slightly implicit, but there is no notion of real time in this definition. You are abstractly mathematically working with the notion of a history, which is only a sequence of invocation and response events. That's it.
I'm saying we sometimes we might want guarantees in terms of the happens before relationship. But can you give an example where we need this linearizability guarantee? This linearizability guarantee is meaningful. Still, we don't actually care about the happens before ordering, and the overlap is defined in terms of some other ordering. So, is that question clear?
Okay, I'm not sure what exactly you mean by happens before ordering here in this context. So, do you mean what I refer to as non-overlapping, or?
So, if let's say there are two concurrent processes, and the process A has not seen the effect of process B, then it might not matter for A and B, even if they are non-overlapping. It might not matter if they are essentially the same, right? Let's say if A and B are A has not seen the effect of B, still A is not the operation of A is not overlapping with the operation of B. So how does it matter if the effect is also overlapping?
I didn't completely follow that, but the nice thing about this notion is it lets you forget about what happens inside the implementation, right? So you can think of the two sides. One is the internals of the data structure implementation that claims linearizability or whatever, right? And what happens inside is completely irrelevant from this definition perspective. What you care as a user of the system is what you observe. So the definition is in terms of what can be observed, right? But the definition of linearizability does so the only meaningful ordering notion here is the ordering of events in the notion of a history. So if in this history you see operation 1 is invoked, operation 1 returns, and then operation 2 is invoked and operation 2 returns, what the implementation cannot know is, from the user's perspective, whether there was any meaningful causal relationship between operation 1 and operation 2. So the user of the system could have done operation 1, and as a result of that, they could have invoked operation 2. That is possible. That could happen on the client side, right? So linearizability makes the worst case assumption, and so we don't know whether there was such a causal relationship. So it tries to ensure that the behavior of the system is consistent with respect to this ordering. So which is why the distinction with serializability arises here. If the system executes as those these two operations executed out of order, then for the client it would be confusing, and which is why you have the definition in this fashion.
So you're saying it's a stricter guarantee than causal ordering, but it might not be. It's just stricter guarantee, and you don't have a real example why it might be more meaningful than causal ordering.
Yes, yeah. You are the ordering guarantee with respect to non-overlapping operations is a stricter guarantee in that sense. From the client or user's perspective, the ordering between those is irrelevant, but the system doesn't know that. So it has to make the worst case assumption it might be relevant and try to guarantee that.
Thanks.
Yeah. Hi.
Can you comment on the cost of linearizability versus serializability in various communication models? So you can say when linearizability is performed in
like message passing model?
Well, no, it is very hard to give abstract characterization without looking at specific problems. But I mean, in general, as phrased, linearizability tries to give us more guarantee, and that can impose some sort of cost. It may not be a theoretical cost, but at least in terms of performance, there could be a performance cost, just in terms of the number of rounds you have to wait and so on. So in fact, there's a talk next week that Kapil Vaswani will be giving. You might see an example there about an instance where you could achieve serializability, linearizability, and there's a difference and some extra weighting required and so on.
I am asking about say cost of linearizability in a shared memory model versus in a message passing model, non-shared memory. So cost of linearizability itself, but in different settings. Is there a difference, and can there be a difference?
Yeah, but then you have to say for what, right? Like for a set, linearizability is a way of converting a sequential specification into concurrent specification. So this question, to make it more concrete, you could say, okay, if you want to do a set implementation, what is the relative cost in shared memory versus asynchronous network and so on.
Yes.
And yes, there can be differences, and it will vary from problem to problem. In fact, so the other dimension you have to take in mind is also, do you want to give these progress guarantees? So if you go, right, I mean, theoretical claims about complexity make sense if you pin down all the aspects, right? So if you say, I want linearizability and I also want, say, this weight freedom or whatever characteristic, and in this model, then what can I do? And similarly, you can ask the same question in a different model, and the results can be different. And I think hopefully you'll see examples over the next 2 weeks also. For example, there are many interesting non-blocking data structures and algorithms that have been devised for a shared memory model. It's not clear how you do something analogous in the network and setting and so on. So,
thank you.
To ask basically what is that we are trading between distributed databases that offer full transactional capabilities versus the key value stores which do not offer all transactional capabilities. Is it just the performance versus the consistency, or there are other issues as well?
Well, I think performance and consistency more or less covers the whole thing, right? So, but yeah, there are clearly many issues in both directions, and I think there's a whole lecture later this week which will talk about some of these weaker consistency models and so on. So hopefully you'll get a more detailed question about, more detailed answer about what are the trade-offs in those lectures. I mean, but yeah, those are two dimensions, and obviously both dimensions you have trade-offs. Okay, so yeah, any other questions?
So when we were defining consensus, what we said that the only thing that we talked about was that the final value we want to choose, it has to be from one of the initial values. But the applications you've seen, like the general problem, there's some logic involved in choosing the values. So, I mean, why didn't we talk about that, or was it just that when defining consensus we just wanted to say that even doing this some simple random assignment is hard enough that doing the other case would be even harder?
Right. So exactly, yeah. From a lower bound perspective, it makes sense to take a simpler version, then it becomes broadly applicable. So that's one reason, but but it works the other way also. To some extent, even if you have this primitive, that is sufficient to implement certain complex things. Like, so for example, replicated state machines. You can use consensus algorithms as a primitive to build many of the other things. So, but yes, there are many variations. Like, so for example, if you are, one of the things I mentioned was distributed transactions. In that context, consensus is to do commit, where a transaction executes on different processes, and the processes have to decide whether they can commit or not. If even one transaction wants to abort, then you should abort. But if all transactions want to commit, then you can commit. So yeah, there are application-specific requirements, but yeah, abstractly, it's not an issue.
How do you differentiate the elasticity and scalability in distributed systems?
I'm not sure if there is any specific technical distinction. I mean, scalability, at least the way I think of it, is looking at the system from the outside. Is it able to meet the outside demand as the outside demand grows? Elasticity somehow seems to be looking inside whether you can add whether you can internally add more resources easily. So, but otherwise, the end effect seems similar. So, I mean, I'm not using them in any specific technical sense. So, okay.
Add to that. So a system that works at 10 nodes and a system that works at 20 nodes and 1,000 nodes, they're all scalable, right? You can build a system that works at 10, then you can rebuild the system for 20, and it'll still scale, or 1,000. That's just scalability. There is a little notion called incremental scalability. How do you go from 10 to 11? Will it scale automatically? And that is what elasticity captures. So incremental scalability and scalability are slightly different. You can build systems that are scalable, but they're not incrementally scalable. And that's the notion that elasticity tries to capture. We used to call it incremental scalability 10 years ago. It's now called elastic. Who do I give this to? Okay, so then since I have them, let's thank the speaker. No, I'll speak on that.